Professor,
Yeah.
did you post a practice review sample?
Yes. I'm going to go over it this morning.
Sorry, I just got back into New York, so I haven't really seen their website.
Yeah. I also sent it out by email.
Okay, I'll take a look at it now.
Okay.
Thank you.
Sure.
How many questions is exam 2?
It'll be like exam 1. I haven't made it up yet, but they're always very similar.
And it's similar to the review sheet?
Well, there are more problems on the review sheet, but they're similar types of problems. But basically, the exam covers everything that we've done. So that's what you're supposed to know. Right?
Okay, thank you.
Sure. Okay, so we'll start. So we're going to go over the review sheet for the exam 2, which is on Wednesday morning. And the first set of problems are just to find some derivatives, which is a fundamental thing to do. So we have x squared times the square root of 1 minus x squared. And we want to differentiate this. So by the product rule, that's the derivative of x squared times the square root of 1 minus x squared plus x squared times the derivative of 1 minus square root of x squared. Let's just do this a little bit on the side. The derivative of square root of 1 minus x squared is 1 minus x squared to the 1/2. So that's 1/2, 1 minus x squared to the 1/2 minus 1, which is a minus 1/2, times the derivative of minus x squared, which is minus 2x. So we get the 2's cancel. We have minus x over the square root of 1 minus x squared. That's what goes here. Minus x over the square root of 1 minus x squared. So this is 2x times the square root of 1 minus x squared minus x cubed over the square root of 1 minus x squared. And it's nice to put this over a common denominator. So we get 2x square root of 1 minus x squared times square root of 1 minus x squared is 1 minus x squared minus x cubed. So this is 2x minus 2x cubed minus x cubed minus 3x cubed over the square root of 1 minus x squared. So at least if I did the arithmetic or the algebra correctly, that's the answer. Let me check. I always like to check. Derivative of x squared is 2x. The derivative of 1 of square root of 1 minus x squared, which is 1 minus x squared to the 1/2, is 1/2. This to the minus 1/2 minus 2x is this. So you get this times x squared is x cubed. Yeah, looks okay. Any questions about this? I mean, you do need to work enough problems that you develop the algebraic skills for calculus. Let's see, b is a trigonometric function, sine of 3x plus 2 cosine x. When we differentiate that, the derivative of the sine is the cosine. So this is the cosine of 3x times the derivative of 3x, which is 3, minus, and the derivative of the cosine is minus the sine times 2. So that's what it is. Okay. C, we're differentiating e to the x plus 3 to the x. And we know the derivative of e to the x is e to the x. What is the derivative of 3 to the x? Well, we write this as 3 is e to the log 3. So if you raise this to the power x, it's e to the log 3 times x. So that's what we're differentiating. And e to a constant times x, when you differentiate it, is the constant log 3 times e to the log 3 times x, or log 3 times 3 to the x. So the derivative of e to the x plus 3 to the x is the derivative of e to the x plus the derivative of 3 to the x, which is log 3 times 3 to the x. And that's the answer. Okay? Any questions about that? Let's see. ABC is followed by D. And we have the function tangent x over x cubed minus 1, which we want to differentiate, and we have to use the quotient rule. So you take the denominator, you square it, and that's the new denominator. And in the numerator, you get the derivative of the tangent, which is secant squared, times the denominator, minus the numerator, times the derivative of the denominator. Just leave it like that. That's the answer. E, we have the function arctangent of x squared. Again, we have to remember the derivative of the arctangent is 1 over 1 plus x squared. So by the chain rule, the derivative of the arctangent of x squared is 1 over 1 plus x squared squared times the derivative of x squared, which is 2x. So we get 2x over 1 plus x to the 4th. And then the last problem is a rational function, 5x plus 6 over 4x plus 5. And these types of functions have a very pretty derivative. Again, we use the quotient rule. So we get 4x plus 5 squared in the denominator. The derivative of the numerator is 5 times the denominator minus the numerator times the derivative of the denominator. So we get 4x plus 5 all squared. In the numerator, what do we have? We have, let me just use the second line. We have 4x plus 5 squared. This is 20x plus 25 minus 20x plus 24. The 20x's cancel. 25 minus 24 is 1 over 4x plus 5 squared. Okay. So even though in your math lab class using Maple or some other program, you know the computer can differentiate every function, it's really important to be able to differentiate things by hand. It's a basic skill in calculus. Okay. All right. In number 2, we have a curve, x squared plus xy plus y cubed equal 11. So I don't know what that looks like, but it describes some kind of curve in the plane. It could go off with whatever it looks like. And we want to find dy dx by implicit differentiation. So if we differentiate this expression with respect to x, that's the derivative with respect to x of x squared plus the derivative with respect to x of xy plus the derivative with respect to x of y cubed. Derivative of x squared with respect to x is 2x. By the product rule, the derivative of xy with respect to x is the derivative of x with respect to x, which is 1 plus what times y plus x times the derivative of y, which is what we want to figure out. And the derivative of y cubed with respect to x, that's the derivative of y cubed with respect to y, 3y squared, times dy dx. So we get 2x plus y plus x plus 3y squared times dy dx. But x squared plus xy plus y cubed, that's equal to 11. So this is the same as the derivative with respect to x of the constant 11, and the derivative of a constant is 0. So we have an equation we can solve. We get x plus 3y squared dy dx, I'll bring this to the other side, is minus 2x plus y. So dy dx is minus 2x plus y over x plus 3y squared. Okay. Now, let's see, x squared plus xy plus y cubed. So let me just write down what we have just done. So this is number 3. We just looked at x squared plus xy plus y cubed equal 11. And we found that dy dx is equal to minus 2x plus y over x plus 3y squared. And what about the point x equal 1, 2? Right? That point in the plane. If you plug it into this equation, you get 1 squared plus 1 times 2 plus 2 cubed. That's 1 plus 2 plus 8. That's 11. So this point, 1, 2, lies on the curve. We don't know what this curve looks like. I mean, Maple will tell us, but we don't know what this curve looks like. But the point 1, 2 does lie on the curve. And at the point 1, 2, what is dy dx? That's equal to minus 2 times 1 plus 2 over 1 plus 3 times 2 squared. That's minus 4 over 13, I believe. Right? If x is 1 and y is 2, minus 4 over 13. So what is the tangent line at the point 1, 2? It's the line given by y is equal to the derivative minus 4 over 13, x minus 1 plus 2. This is minus 4 over 13x plus 4 over 13 plus 2. So y equals minus 4 over 13x and 26 plus 30 over 13. Okay. Any questions about that?
I have a question. Where did the x minus 1 come from?
Well, so the tangent line, so we have the point slope formula. The line through the point x1 comma y1 with slope m is y equals m x minus x1 plus y1.
Can you move the paper, please?
Sure.
Thank you.
So this is a basic formula from high school algebra or pre-calculus, right, that we've used a lot already. That's how you find the tangent line. So in this case, x1 is equal to 1, y1 is equal to 2, and minus 4 over 13 is the slope. So let me see if I can use the magic of Maple to actually draw you a picture of what's going on. So what I'm going to do is try to share the screen for a moment. So can you see this Maple worksheet?
Yes.
Okay, so there's a package for plotting. And what I'm interested in is the curve x squared plus x times y plus y cubed equals 11. And I want to see what the graph looks like. So the command in Maple to plot an equation of this sort is the implicit plot. So that's what the curve looks like, or at least part of the curve. And notice here is the point 1, 2. And what I claim is the tangent line it's y equals minus 4 over 13 times x plus 30 over 13. Minus 4 over 13x plus 30 over 13. So let me go back and let's see if I can plot the curve and the tangent line together. Fantastic. So everybody, I hope you can appreciate this. It's quite beautiful, and it shows how powerful Maple can be with just a few commands. This is what this curve looks like. On the curve, here's the point 1, 2, and this line is tangent to the curve at the point. Let me do it to scale. Yeah, that's really what it looks like when it's drawn to scale. 1, 2, that's the point. And this line is the tangent line. And yeah, that's what it looks like. So that's kind of nice. Hope everyone enjoys that. Let's go back. Okay. It's always nice when you can draw a picture and confirm your work. So that was 3. Number 4, we have a function y equals 1 plus x cubed, 1 plus 2x squared, 1 plus 3x to the 5th, and we want to use logarithmic differentiation to find the derivative. That means we take the log of y, so that's the log of this whole expression, the log of a product is the sum of the logs, so that's the log 1 plus x cubed plus the log of 1 plus 2x squared plus the log of 1 plus 3x to the 5th. And when you have the log of something raised to a power, you can take the power in front. This is 3 times the log of 1 plus x plus 2 times the log of 1 plus 2x plus 5 times the log of 1 plus 3x. Right? That's the first step. So if we differentiate with respect to y, with respect to x, the derivative of log y with respect to x, the derivative of log y with respect to y is 1 over y times dy dx. On the other hand, that's equal to the derivative of this expression. So we get 1 over y dy dx. We differentiate this, we get 3 over 1 plus x plus 2 over the derivative of the log of 1 plus 2x is 1 over 1 plus 2x times the derivative of 1 plus 2x, which is 2, plus 5 times the derivative of the log of 1 plus 3x, that's 1 over 1 plus 3x, times the derivative of 1 plus 3x, which is 3. So dy dx is equal to, just multiply through by y times 3 over 1 plus x, plus 4 over 1 plus 2x, plus 15 over 1 plus 3x. All right. Any questions? Questions?
Professor,
Yes.
you don't have to simplify.
I'm sorry. Can you speak up? I didn't hear what you said.
I said we don't have to simplify the expression.
No, it's okay like this.
Okay.
Yeah. In fact, to add all those fractions actually gives you just something which I think is more complicated. But at this point, you can certainly stop. Okay. The next problem is a related rate problem. So we have a cube. And let's say the side of the cube is x. So the volume as a function of x is x cubed, and the surface area as a function of x, well, each side's a square of side x, so each side has area x squared, and there's 6 sides, front, back, top, bottom, left, right, 6x squared. So this is what we know from whenever, and we're told the edges of the cube are expanding at a rate of 4 centimeters per second. So dx dt is 4 centimeters per second. How fast is the volume changing when each edge is 12 centimeters? So dv dt is dv dx dt. What is dv dx? 3x squared. What is dx dt? 4. So this is 12x squared. And when the edge is 12 centimeters, this is 12 times 12 squared, which is 12 cubed, which is, what is 12 cubed? $19.28, perhaps. No, $17.28. Centimeters cubed per second. And how fast is the surface area changing? Well, dA dt, this is the dA dx dt. When you differentiate a with respect to x, you get 12x times 4, which is 48x. And when x is 12, this is 48 times 12. Which, at least today, might be 476 square centimeters per second.
Professor,
Yeah.
where did you get the 12x?
A is 6x squared. dA dx is 12x.
Got it. Thank you.
Right? dA dt by the chain rule is dA dx dx dt. The dA dx is the 12x, and dx dt is the information we were given at the start. So this is an example of a related rate problem. Right? Two quantities are related. For example, the side of the square and the volume. We know how fast the side of the square is changing, and calculus tells us how fast the volume is changing. Okay, problem 6. We have a function g of t equal t cubed minus 3t squared plus 5. And we're looking at just on the closed interval from -2 to +2. And we want to find the absolute extrema. Which means the absolute maximum and the absolute minimum. So we have to first find the critical points. Of g of t. We differentiate. We get 3t squared minus 6t, which is 3t times t minus 2. And this is equal to 0 when t is equal to 0 and 2. So those are the critical points. And we need to find the value of the function at the critical points and at the endpoints of the interval, because those are where the absolute maximum and minimum will occur. So we have the different values of t, 0, 2, and the endpoints. Well, 2 is already one of the endpoints, minus 2. And for those values, we have to calculate g of t. When t is 0, g of 0 is 5. When t is 2, this is 8 minus 12, that's minus 4, plus 5 is 1. When t is minus 2, this is minus 8 minus 12 is minus 20, plus 5 is minus 15. So let me just check. When t is 0, this is 5. When t is 2, I have 8 minus 12, that's minus 4, plus 5 is 1. When t is minus 2, this is minus 8 minus 12, minus 12 is minus 15. So the absolute maximum is at the point 0, 5, and the absolute min is at the point minus 2, minus 15. Actually, let me take advantage of Maple once again. Let's see if I can get back into it. Here we are. So we have the function G of t is t cubed minus 3 times t squared plus 5. And suppose I plot G of t going from -2 to +2. There it is. And you can see here is the absolute minimum at -2, -15. And the absolute maximum is here at 0, 5. If we were to draw this to scale, it looks like that. It's even more clear. So this is now drawn to scale. So from -2 to 2, this is the minimum, absolute minimum in this interval, shoots up to 5 at 0, turns around, comes down, but that's the absolute max and that's the absolute min. Yeah, pretty good. It's fun having Maple. Couldn't do this in the classroom. Okay. Any questions about this so far? All right. In problem 7, we have the function f of x equals x squared over x squared minus 9. Find the critical numbers. So f prime of x, this is x squared plus 9 squared if we use the quotient rule. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. I get 2x cubed minus 2x cubed. So this is minus 18x over x squared minus 9 squared. So the critical numbers are the numbers where the function either does not exist or the derivative is 0. So the derivative is 0 when x equals 0, and it doesn't exist when the denominator is 0, which is a 3 and minus 3. So those are the critical numbers. And now let's just take a look at this. Suppose this is x equals 0, x equals 3, x equals minus 3. So except when x is plus or minus 3, this is positive. So the sign of the derivative is the opposite of the sign of x. So for x between 0 and 3, the derivative is positive and the function is increasing. For x greater than 3, it's negative, and the function is decreasing. When x is greater than 3, also, the derivative is negative. The function is decreasing. When x is negative, this is positive. So in these two regions, the derivative is positive, and the function is increasing. So the open intervals in which the function is increasing are minus infinity to minus 3 and minus 3 to 0. The function is decreasing on the interval from 0 to 3 and 3 to infinity. Where are the relative extrema? Function is increasing, increasing. Now it's decreasing and decreasing. So there's a relative maximum at x equals 0, because the function is increasing and then it's decreasing. Okay. Any questions about that? Let me draw the picture. Me meaning, let Maple draw the picture. Let's see. So in this problem, the function f is equal to x goes to x squared divided by x squared minus 9. And let me try to plot f of x. So it doesn't work too well because you have vertical asymptotes at plus and minus 3. Let me try something different. Let's say x goes from minus 5 to 5. Y goes from minus 5 to 5. Ah, now we have it a lot better. Let me extend a little bit. There we go. Now that is fantastic. So you see, from minus infinity to minus 3, it's increasing. On the open interval from minus 3 to 0, it's increasing. You have a relative maximum at 0. From 0 to 3, it's decreasing. And from 3 to infinity, it's also decreasing. Right? That's what our function looks like. Okay. So with Maple, you have this beautiful picture of what's going on. Okay. Good. That's number 7, which means it is followed by number 8. So number 8, f of x is the function 4 over x squared plus 1. And we want to find the points of inflection and the open intervals where f of x is concave up and concave down. So to find concavity, we need the second derivative. So we start with the first derivative. First derivative is, let's see, this is 4x squared plus 1. Well, I'll use the quotient rule. X squared plus 1 squared. The derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator, which is 2x. So this is minus 8x over x squared plus 1 squared. And then what is the second derivative? We get the denominator squared. So when you square a square, you get the 4th power. Put the minus sign in front. The derivative of 8x, which is 8, times the denominator, minus 8x times the derivative of the denominator, which is 2 times x squared plus 1, times the derivative of x squared plus 1, which is 2x. So this is minus, I can factor an x squared plus 1 out of the numerator. That makes this a 1 and makes this a 3. So this is x squared plus 1 cubed. So I have here 8 times x squared plus 1 minus 2 times 2 is 4 times 8 is minus 16x squared. This is 8x squared minus 16x squared. That's minus 8x squared plus 8 over x squared plus 1 cubed. So that's equal to minus times minus is plus 8 times x squared minus 1 over x squared plus 1 cubed. So that's my second derivative. The denominator is always positive. The second derivative is positive. if x squared minus 1 is greater than 0, which means x squared is greater than 1, which means either x is less than 1 or x is less than minus 1. So this is where the curve is concave up. And the derivative is negative if x squared minus 1 is less than 0, x squared is less than 1, which means x is between plus 1 and minus 1. And here, it's concave down. So up from infinity to minus 1, this is concave up. And from 1 to infinity, it's also concave up. And from minus 1 to 1, it's concave down. All right. Let's see. Questions about that? Let's look at the picture. Share screen to Maple. So in this problem, the function f of x is f of x equals 4 over x squared plus 1. And let's plot f of x. There it is. Okay. So this curve is concave up until you get to x equal 1. Then you have an inflection point. So I should have just, at x equal 1, you have an inflection point. Here it's concave down. And then again, starting at x equal 1 to infinity, it's concave up again. Right? That's what the curve looks like. Concave up, concave down, concave up. That's really nice. And I should have said then we have inflection points where the concavity changes, which is at x equal 1 and x equal minus 1. Okay. Nice, I believe. In problem 9, we want to find some limits. The first is the limit of 4x minus 1 over the square root of x squared plus x. And we can simplify this a little bit as follows. Factor out an x squared in the under the square root sign. You get x squared times 1 plus 1 over x. So that's 4x minus 1. And the square root of x squared is x times the square root of 1 plus 1 over x. In fact, if I factored an x out of the numerator also, this will be x times 4 minus 1 over x times the square root of 1 plus 1 over x. And the x's cancel. So I can rewrite this as 4 minus 1 over x over the square root of 1 plus 1 over x. And if I write it like that, it's easy to see what the limit is. The limit as x goes to infinity of 4x minus 1 over the square root of x squared plus x That's the same as the limit as x goes to infinity of 4 minus 1 over x over the square root of 1 plus 1 over x. As x goes to infinity, these terms go to 0. So the limit is 4 over the square root of 1, or 4. Okay. The second limit, 5x cubed minus 10x plus 3 over 2x cubed plus x squared minus 9x minus 1. I want to factor x cubed out of the numerator and the denominator. This becomes 5 minus 10 over x squared plus 3 over x cubed over x cubed times 2 plus 1 over x minus 9 over x squared minus 1 over x cubed. And the x cubes cancel. So the limit as x goes to infinity of this rational function is the limit as x goes to infinity of 5 minus 10 over x squared minus 3 over x cubed over 2 plus 1 over x minus 9 over x squared minus 1 over x cubed. These all go to 0, and we're left with just 5/2, which is just an instance of the general rule. If you have a rational function, a quotient of polynomials where the numerator and denominator have the same degree, the limit as x goes to infinity is just the ratio of their leading coefficients. 5/2, that's what we see. Okay. Questions about that? Oops, this was number 9. So problem 10, this is an optimization problem. Find the dimensions of the largest rectangle that can be inscribed in a semicircle of radius 10. So this is the semicircle of radius 10. The circle of radius 10 is x squared plus y squared equals 10 squared, or 100, or y squared equals 100 minus x squared. We're taking the semicircle in the upper half plane. Y is the square root of 100 minus x squared. So for any point on the circle, x, y, this is what y is equal to. And if you take a point on the circle and you drop the perpendicular, draw the horizontal, drop the perpendicular again, this is minus xy. And once you pick the point xy, that determines the rectangle. What is the area of this rectangle? A, so this is x and this is minus x. The area of the rectangle is the base times the height. From minus x to x is 2x, and the height is y. But of course, y is equal to this. 2x times the square root of 100 minus x squared. So once you pick x, that determines y, it determines the rectangle, and that's the area. So to find the largest rectangle, you differentiate this function. You want to find the maximum. You differentiate this function of x and find the critical numbers. So dA dx, that's the derivative with respect to x, of 2x times the square root of 100 minus x squared. The derivative of 2x is 2 times the square root of 100 minus x squared, plus 2x times the derivative of 100 minus x squared. That's a half, 100 minus x squared to the minus a half, times the derivative of 100 minus x squared, which is minus 2x. So this is equal to 2 times the square root of 100 minus x squared. This 2 and this 2 cancel. I get minus 2x squared over the square root of 100x squared. And if I put this over a common denominator of a square root of 100 minus x squared, I get 2 times 100 minus x squared minus 2x squared. Which is 2 over the square root of 100 minus x squared. And I get 100 minus x squared minus x squared, 100 minus 2x squared, if I did this arithmetic correctly. And this is equal to 0 precisely when 2x squared equals 100. So x squared equals 50. So x is the square root of 50, which is 5 root 2. So when x is equal to 5 root 2, a of 5 root 2 is equal to, this is my formula for the area, 2 times 5 root 2 times the square root of 100 minus this squared. So that's 10 root 2 times the square root of 100 minus 50, which is 10 root 2 square root of 50 is 5 root 2. So this is 100, evidently. My arithmetic is right. And that's the maximum area. Let's see. From here to here is 10 root 2. Y is 5 root 2. 5 times 10 times 2 is 100. That's the area. Okay. Any questions about this?
Professor, please, can I see the previous paper once more?
Right. So,
Yes.
yep.
Thank you.
Okay. Number 11, find the points on the graph closest to the point 0, 1. So we have the parabola y equals 3 minus x squared. So that parabola has its vertex. Let me draw it a little bit bigger. has its vertex at 3. When x is 1, it takes on the value 2. And when x is minus 1, it takes on the value 2. And it's equal to 0 at the square root of 3, which is minus 1.7. So this parabola kind of looks like that. And here is the point 0, 1. And on the curve, you have the point xy. And there's a certain distance from 0, 1 to the point xy. And we want to find the point on the curve which is closest to 0, 1, right? Like this point is 2 units away. This point is whatever it is away. We want to find the point. So find the point xy on the parabola, on the curve, closest to 0, 1. So let's call this function d, the distance. What is d? D, well, we know the distance formula from pre-calculus. The distance from this point to this point is the square root of x minus 0 squared plus y minus 1 squared. That's the square root of x squared plus y minus 1 squared. That's the distance. And if we like, we can take the distance squared just to get rid of the square root, because this is small when what's under the square root sign is small. X squared plus y minus 1 squared. And we want to minimize this. So we have a function, let me call it capital D of x, which is x squared plus y minus 1 squared. And the reason I can write this is a function of x, because on the parabola, y is 3 minus x squared. Y minus 1 is 3 minus x squared minus 1, which is 2 minus x squared. So this is x squared plus 2 minus x squared squared. So this is the first step, but it's in some sense the most important, is translating the words of the problem into an algebraic equation. We have the parabola y is 3 minus x squared. Take a point on the parabola with coordinates x, y, but of course this is the same as x comma 3 minus x squared. And what's the distance from here to here? Well, the distance squared is x squared plus 3 minus x squared minus 1 squared, or 2 minus x squared. And it's easy enough just to simplify this. This is x squared plus, and when I square that, I get 4 minus 4x squared plus x to the 4th. So that's x to the 4th minus 3x squared plus 4. So my distance d of x is x to the 4th minus 3x squared plus 4. The derivative is 4x cubed minus 6x. So that's 4x times x squared minus 3/2. And that's equal to 0 at x equals 0, or x equal plus or minus the square root of 3/2. What's the second derivative? 12x squared minus 6. These are the critical numbers. The second derivative at 0 is minus 6. So this is a relative maximum by the second derivative test. Where the second derivative is negative, the function has a relative maximum. The second derivative at plus or minus 3/2 is 12, plus or minus square root of 3/2. 12 times 3/2 minus 6, That's 18 minus 6, or 12, which is positive. So here we have a relative minimum. So the points closest to this on the curve are the points where x is equal to plus or minus the square root of 3/2. And y.
Professor, shouldn't the 3/2 be in the square root form when it's inside 12? Oh no, it cancels out. Okay, never mind. I answered my own question, sorry.
Okay, anyway, well, if I did this correctly, the method is right. And if I did the algebra correctly, that's the answer at these 2 points. X equal plus or minus square root of 3/2, and y is equal to 3/2. And then the last problem, number 12, is an optimization problem. Find positive numbers, x and y, such that the sum is equal to 12 and the product, x times y, is as large as possible, is a maximum. So I need to reduce this first to a function of just one variable, and we make the initial observation. If x plus y is 12, then y is determined by x. So y is always equal to 12 minus x. And x and y are positive, so x and y are both between 0 and 12. And xy is then x times 12 minus x, which is 12x minus x squared. Okay. That's my function. I'll call it p of x for the product. So p of x is 12x minus x squared. We want to maximize that. P prime of x is 12 minus 2x, and that's equal to 0 when x is equal to 6. The second derivative is minus 2, which is negative. So x equals 6 is a maximum. And when x equals 6, y is equal to 6. So if two numbers add up to 12, their product is a maximum when x equals y equals 12. Okay. Any questions? So that is the entire review sheet.
I have a question. What were you saying? If two products add up to 12?
No, not two products. What do you mean? If two numbers add up to 12. So,
Oh, okay.
right, we want to find positive numbers x and y whose sum is 12. And we want to choose the two numbers so that the product xy is a maximum, is as large as possible. And it turns out you get the maximum product when x equals y equals 6. Okay. Okay, so the exam is 9 o'clock on Wednesday morning. I'll post it a little bit before 9 o'clock on Blackboard and in the assignment section, just like the last exam. Class period is normally an hour and 40 minutes, but you'll have 2 hours. Of course, you have to if possible, convert your exam sheets to PDF file and upload them. When you do that, please make sure that you do the problems in order, right, on the paper. You know, you can decide you want to do number 5 first and number 1 second, but if you do them on separate pieces of paper, then you, at the end, you put the problems in order. I want the problems to be in order on your exam paper. Also, there are 1 or 2 people who weren't able to figure out or weren't able technically to make a PDF file, and they photographed their pages. Make sure when you do that, the pages are upright. They're in the right, they're not sideways. It's not horizontal. It's just the way it's supposed to be. And also, I need to see your work. It's not enough just to write down the answer unless the problem's completely trivial. Like if I ask how much is 2 plus 3, you can just write down 5. But on other problems like the ones I've just been doing, make sure your work is on the paper. I need to be able to see your work. Okay. Any other questions? Any questions at all? I will set up like a Zoom office hour tomorrow if you have any last minute questions. And I'll send out an email with the time and the Zoom login. Okay. If no one has a question, then we are done for today. We'll be back next in 2 days, Wednesday morning. Okay, bye everybody.